This video is part of an online course on algebra and will be about equivalence relations. There are many different types of relations, and for the most important ones we have names. Names are supposed to capture entire ideas within a word, so it is very good to have names for most commonly used relation, so that whenever you hear the word, the idea pops up in your head. The first and simplest type of name that you want to give is for a relation such that A is always related to A. Such relations are called reflexive relations. Symmetric, as the name suggests, means that whenever the element A is related to the element B, automatically the element B is related to the element A. Transitivity means if A is related to B and B is related to C, then automatically A is related to C. A relation R is said to be antisymmetric if whenever A is related to B and B is related to A, then it forces A to be equal to B. So, notice that this formulation is somewhat weird. You might think that an antisymmetric relation is one in which if A is related to B, then B cannot be related to A, but the way this is formulated here is what is the most useful formulation. So, keep that in mind. Finally, a relation R is irreflexive if A related to A is false for all A. As the name suggests, it is just the opposite of reflexive. Now, an order relation is a type of relation which satisfies several of the properties that I listed in the last slide. So, an order relation, also called a partial ordering, is a binary relation that is reflexive, antisymmetric and transitive. We say that the ordering is partial because not all elements need to be comparable. In case all elements are comparable, we have a total order. So, some explanation is in order, but before that let us take a few examples so that the concept is concrete, then the explanations will make more sense. The relation less than or equal to are natural numbers, integers and the reals. Now, in this case clearly we have reflexivity because A is always less than or equal to A, and we also have transitivity. If 2 is less than or equal to 3 and 3 is less than or equal to 4 means that 2 is less than or equal to 4. We also have transitivity in an obvious way, and we have antisymmetry. If A is less than or equal to B and B is less than or equal to A, then automatically A is equal to B. Now, notice one thing, this relation of being less than or equal to on natural numbers, integers and reals, this is a total ordering, meaning that any two elements you take in the natural numbers, either A is less than or equal to B or B is less than or equal to A. Note, it can happen that both are true, in which case A will have to be equal to B, but nevertheless the point I want to emphasize is no matter which two elements in the integers you take, they will be comparable with each other. Now, a sad part, an unfortunate thing has happened. The standard less than relation on integers or numbers, natural numbers or reals, this is not a partial ordering, because it does not have the property that if A is less than B and B is less than A equal to B. The crucial issue is that it is not reflexive. So, if it can never happen that A is less than A, right. So, notice I made a slight error. What I wanted to emphasize is, if A is less than B, it can never happen that B is less than A. Notice antisymmetry says that if you have a relation R which is antisymmetric, A related to B and B related to A means A is equal to B. Here the second case can never happen. In particular, it is irreflexive. So, it cannot be an ordering. So, thanks to some quirks of history, it happens in mathematics that some common notations will not gel well with other definitions. So, a trade off has to be made. This combination of properties antisymmetry, transitivity and reflexivity turns out to be the most useful thing to consider when you are considering orderings. So, therefore, we prioritize this. So, always remember that order relations are modeled after less than or equal to and not less than. Now, let us come to the second example of the order relation, which is the notion of subset on a collection of sets. So, the situation here is you have a collection of sets, let us say F, a family of sets, and on this set we are going to put a relation where we say A is related to B if A is a subset of B. Now, clearly this relation is reflexive. A is always a subset of itself and it is antisymmetric, because A subset of B and B subset of A automatically means A equal to B. In fact, this is the standard way by which you prove two sets are equal. And finally, transitivity is rather obvious in this relation. Now, this is not a total ordering in general. If your family of sets has two sets, for instance like 1, 2 and 2, 3. If both of these are there in F, then it is not true that 1, 2 is a subset of 2, 3. It is also not true that 2, 3 is a subset of 1, 2. So, neither of the relations hold. So, this is not a total ordering. These two sets are simply not comparable with each other. Finally, look at the division relation on integers, that is, we say a number A is related to B if A divides B. This is clearly reflexive because A divides itself. It is antisymmetric as well. If A divides B and B divides A is equal to B. Well, not quite. A is equal to plus or minus B. So, to be 100% correct, I must say this on natural numbers, not really integers. On integers, in any case, there is a deeper objection, because what will you do if you divide by 0? My iPad will just blow up and we do not want that to happen. So, technically it is on the natural numbers. Now, we will revisit order relations when we study natural numbers and mathematical induction. There you will understand that ordering is very crucial and it is one of the tools that make induction work. Okay. Now, we come to arguably the most important type of relation, namely an equivalence relations. Among all relations, equivalence relations are the most important. Many constructions that we will see in this course and you will see in other courses like geometry are based on the idea of quotienting a set by an equivalence relation. By the end of this video, you will understand what quotienting means. So, what are equivalence relations? Well, they are modeled on equality, as the name suggests. Equality has three key properties. On any set of objects, equality is always reflexive. An element is always equal to itself, an object is always equal to itself, and if an object is equal to object A is equal to object B and object B equal to object A, then object A and B are the same, right. So, that is transitivity. So, symmetry says that if object A equals B, then automatically object B equals A, and transitivity says if object A equals B and B equals C, then A and C are equal. We are going to lift these properties up to an arbitrary relation and call the resultant relations as equivalence relations. So, how does it go? Let A be any set, and this symbol tilde is typically what is used for an equivalence relation. Some common alternatives are tilde, but with an equality. This is also commonly used. In this course, I will just stick to tilde, it is simpler, slightly less amount of writing to do. So, we have let A be a set and tilde be a relation on A. We say that tilde is an equivalence relation if it satisfies the following three properties, namely reflexivity, A is always related to itself, symmetry, if A is related to B, then B is related to A, finally transitivity, if A is related to B and B is related to C, then A is related to C. So, as you can see, we have just taken the three key properties of equality and just generalized it to an arbitrary relation. Let us see some examples. Well, as you can expect, the first example is rather trivial, that just says that equality is an equivalence relation. Obviously, it better be, because that was the model for our equivalence relation. The second one is a non-trivial one and is very interesting. Now, way back when you were in 7th standard or something, or even before that, depending on which school and which curriculum your school subscribed to, you would have learned something called the rational numbers. The rational numbers, as we all know, are quotients of integers where the denominator is not allowed to be 0. For instance, we have fractions like 1 by 2 and 2 by 4. They look different. Well, the first one has a 1 on top and a 2 and a bottom, the second one has 2 on top and 4 at the bottom, but ultimately they both are the same rational numbers. 2 by 4 is just another way of writing 1 by 2. So, this suggests that we take the set of all such fractions. Do not ask me now what exactly a fraction is, that you will understand at the bonus video for this particular week, what exactly these fractions are. So, if you take two such fractions, we can declare them to be equal if AD equals BC. In other words, when you can cancel off, reduce them into the most primitive forms, then both will be the same fraction. So, on the collection of all fractions, we can put a relation that says that two fractions A by B and C by D are equivalent if AD equal to BC, then each rational number, if you think about it, is expressed in an infinitely many ways as fractions, and what this equivalence relation will allow us to do is to treat any fraction that represents a rational number with equal status. Okay. So, in a few slides, be patient, in a few slides you will understand that what equivalence relations really allow you to do is to treat the entire collection of fractions that represent a single rational number. It will allow you to treat that itself as a new entity. So, that is the power of equivalence relations. It allows you to identify certain elements of a set which are related to each other by this specific type of relation. Now, the next one is probably the most important one in terms of applications, is the congruence modulo 2 on integers. As the name suggests, there is a congruence modulo n, without which you cannot really do modern number theory or cryptography. Let us just take the simplest case, that is congruence modulo 2 on integers. We say, note the relation is really complicated, you write it as A, this triple equal to B mod 2, that is the actual relation, that says that A is congruent to B mod 2. In other words, two numbers A and B are related if A is congruent to B mod 2, and that happens precisely when A minus B is even. Now, notice I am skipping a few checks both in the previous example and I am going to skip checks in this example as well. You really have to sit down, spend a few minutes and check that this one is really an equivalence relation, and same with here. Okay. So, congruence modulo 2 is also equivalence relation on integers. Let us look at the next one, cosets in group theory. Well, group theory we will revisit, we will visit for the first time, in fact in a couple of weeks, but we will not really go into cosets now, that is part of algebra 2 which is going to come later. This cosets in group theory, this is a far reaching generalization of the previous example. I am not going to say anything more because I simply do not have the technology to say it now, but why I am saying this is I want to anticipate what is going to come, not just in the near future, but also in the far future. I want to say that several constructions in mathematics are coming out of equivalence relations, and here is one example, cosets in group theory. I am not expecting you to understand what a group is or a coset is, you simply do not know yet, but you will see that you can sort of break up a group into cosets in a natural way, and that gives a construction of what is called a quotient. We will see the basic notion of quotients in the next few videos. Graph connectivity, again if you are familiar with graphs, these are not the graphs that you drew in school on graph paper, these are vertices which are connected by edges. If you have taken a course on discrete mathematics, you will know what I am talking about. We can say two vertices in a graph are equivalent if they are connected by a path. Again, this example is not really to illustrate the concept of equivalence relation, but rather it is propaganda to say that equivalence relations arise in several branches of mathematics. Now, as I said, these examples illustrate how equivalence relations arise in various contexts. Let me give you examples from geometry. The last slide was bereft of any geometry. Well, believe it or not, you have been exposed to equivalence relations quite extensively, not just when you studied rational numbers, but when you studied geometry. Well, when do you say two triangles are congruent? Well, as you all know, that means all sides and all angles are equal. Well, look at the set of all triangles in the plane and you declare that two triangles are equivalent if they are congruent. Now, there is actually no need to even check that this is an equivalence relation, because two triangles being congruent means all sides and all angles are equal. If all sides and all angles of these two triangles are equal, then obviously the other way around is also true, and transitivity is equally easy to verify. Similarly, no pun intended, the notion of similarity on congruence on triangles is also an equivalence relation. So, these are two familiar equivalence relations in which you have studied extensively in your 8th, 9th, 10th standards. I do not know exactly which classes, but this has been there lurking in the background for all these years. Well, finally, let me consider another equivalence relation on R2, and this is going to illustrate what is going to come in the rest of this video. Again, let us model the plane as usual as R2 and declare 2 points x, y and u v are equivalent if x squared plus y squared equal to u squared plus v squared. Now, you can tediously verify that this is an equivalence relation. It is not hard, it is tedious. Tedious just means that you will have to spend some time writing it out. So, the only difficult thing to check would be transitivity. You can do it, work out all the gory details, and in the process consume precious resources of paper and pen, ink that is. Or you can be slightly clever and you can observe what this condition is really trying to tell you. We are just declaring 2 points in R2 to be equivalent if they lie on the same circle centered at the origin. So, we have this visual representation, we have various circles around the origin and 2 points are related precisely when they belong to the same circle. So, all points in this circle of radius R3 are related to each other, all points in the circle of radius R2 are related to each other, all points in the circle of radius R1 are also related to each other, and the point 0 is lonely and it is alone, it is not related to anything else. Now, if you think about this picture for a second, you notice that these circles centered at the origin are really breaking up the plane into smaller pieces. You have just written the plane as a union of various circles. That is going to lead us on, it is going to segue to the next idea, but before that let us see some non-examples. Why do you want to see non-examples? Well, you can to have a full understanding of the definition and to be not misled into thinking that all common relations are equivalence relations, it is important to see some non-examples. Well, an order relation is almost never an equivalence relation. Notice I did not say never, I said almost never, and it is up to you to justify why almost. For example, on the natural numbers, we have 2 is less than or equal to 3, but obviously 3 is less than or equal to 2 is false. Order relations are after all antisymmetric. So, it is highly unusual that they will be symmetric as well, except in a very particular situation. Here is another interesting non-example. Consider the natural numbers once again and declare that a and b are related if they have a common factor greater than 1. So, a and b are related if there is a common factor that is higher than 1. Now, notice that this relation is clearly reflexive because okay. So, this relation is clearly reflexive if a is not equal to 1. So, let us just ignore 1 for the time being. It's a slight oversight, but 1 is going to play a pesky role, but it is not really important. I want to illustrate a different point. So, it is reflexive if A is not equal to 1, and it is clearly symmetric. If you take two numbers A and B and they have a common factor greater than 1, then obviously A is related to B implies B is related to A, but it is not transitive. Well, how can that happen? Well, consider for instance 4, 6 and 9. 4 is related to 6 because they have a common factor higher than 1, that is 2. 6 and 9 are related because they have a common factor higher than 1, that is 3, but 4 and 9 are not related. There is no common factor between 4 and 9 that is greater than 1. So, this is an example of a relation which is symmetric and reflexive, almost reflexive, just ignore 1, then but transitivity is lacking. Okay. Now, let me give you one real world example. After all, the name relation suggests that there should be some interesting examples amongst human beings and some typical relationship. Okay. Let us take the relationship. We say A is related to B if A is a friend of B, right. Now, this relation is not reflexive. Why is that? Well, as we all know, sometimes we are our own enemies, we are our own greatest enemy also sometimes. So, it is clearly not reflexive. Well, it is not transitive, certainly. I can be a friend of some other person, that person can be a friend of some other person, and I have no idea what the third person is, that can happen. Sadly, this relation is not symmetric as well. It is not reflexive, it is not transitive, it is not even symmetric. Well, we all know, you could be thinking you are a good friend of somebody else, well, that person is not really a friend of yours and he just wants to stab you in the back at the nearest opportunity. So, on this sad note, let us move on to happier matters. How to break up a set into equivalence classes. Okay. So, for that we first need to see what the definition of an equivalence class is. An equivalence class is defined whenever you have a relation on a set. The equivalence class of an element A in A is you just take a giant box and in that box put all the elements B that are related to A. So, this box, that is why the notation is box A. Another common notation for those who want to write more, but be even more clear, is they will write box A with a tilde in the bottom to suggest that the relation comes from tilde, but since I am going to consider only one equivalence relation at a time, it is very clear what the equivalence relation is going to be at all times. So, I will ignore the tilde. So, box A is the equivalence class of the element A. It consists of the set of all elements B in A such that A is related to B. Now, notice that it is quite possible that box A is equal to box B even if A is not equal to B. The best way to understand this is to think about the circles example. If I look at any particular circle, then the equivalence class of that particular point is the entire circle of the radius which this point is away from the origin, right. But if I had chosen any other point in the circle, in the same circle, box of that point is exactly the same circle. So, the element A in box A is called a representative, okay, and the collection of all equivalence classes is denoted A, you write divided by the relation, it is read as A quotient, read A quotient of A modulo tilde, okay. Now, most often you just say A modulo tilde, that is what you usually say, but more correctly it is A quotient of I mean read A quotient of A, I think I put two A's, read A quotient modulo tilde, okay. Now, I am just going to elaborate that remark I made. It can happen that you have multiple representatives for the same equivalence class. So, that is why we say A is a representative of box A and not the representative of box A. Okay. So, representatives are very far away from being unique. It can happen that a single equivalence class is represented by 10,000 different representatives. Okay. Let us see some examples. In the case of equality, which is the simplest type of equivalence relation, the equivalence class of an element is just the singleton set A. Okay. In fact, these are the only equivalence classes. In equality, the only equivalence classes are singleton sets. In the case of rational numbers that we saw, the equivalence class of a fraction A by B is the set of all fractions C by D such that AD equal to BC. So, this is what I meant by you can represent a single rational number by the equivalence class of all fractions. You just put all the fractions that represent a particular rational number, put it in a box and say that is the rational number. That is essentially how the rational numbers are constructed from the integers. In the case of congruence modulo 2, the equivalence class of an integer A is the set of all integers B such that A minus B is even. In less complicated words, there are only two equivalence classes, and I urge you that you sit down and check it right away, pause the video, check it right away before proceeding, that the two equivalence classes are the even integers and the odd integers. So, this is just a very complicated way of saying that the only elements that are related to each other are those that are all even and those that are all odd. Okay. Now, the aim is to show that if you have an equivalence relation on a set, then you can break up that set into multiple pieces. Each piece is disjoint from every other piece, and the union of all these pieces is exactly the whole set. The best picture to keep in mind is the concentric circles example that we saw, where we are breaking up the plane as a union of circles. Now, to make this precise, we need the notion of an index family of sets. Well, an index family of sets is a collection AI where I ranges over some index set I. Well, this does not really make a lot of sense. Let us elaborate what this means. So, as I said, almost always you have a set from which you construct all other sets which you are going to study in that present context. So, let us U be the universal set in the present context, that is all the sets that you are going to study come from U in this present context. This is a course on algebra, so sometimes this will be the set Z, sometimes it will be the set Q, sometimes it will be the set R, sometimes it will be an arbitrary but fixed set G called a group, or a set R ring or a V vector space, but you have a fixed set. And let I be any non-empty set called the indexing set. You can index sets by any element you want from any set. Then an index family of sets is a function f from I to the power set of u. In other words, the index family f is nothing but the image of this function f. That is, what you are really doing is you want to refer to elements of the set that you are considering by using elements of I. So, the simplest case is, for instance, when you have, let us say, I mean I will give an example in a while, but to make sense, what we are really doing is we want to refer to subsets by names, and the names are going to be given by elements of I. Okay. Now, typically but not always, this I is going to be the set of natural numbers. That is typically the case, but not always. Okay. Another crucial point that I want to make is that f need not be injective. So, that means there could be several sets in your index family which have multiple names. It can happen that if you are indexing by natural numbers, A1 is equal to A3, right. As elements of the set f, they are the same element, but they have multiple names. So, it can happen that ai equal to aj even when I is not equal to j. Okay. Now, let us take a simple example to make this complicated definition sensible. So, let us take a function f from natural numbers to power set of natural numbers given by f of n equal to x in n such that x is less than n. That is, the index family f n is the collection of all initial segments of the natural numbers. Now, notice that f of 1 is actually the empty set. It is quite possible, in fact, it is often the case that this family f has the empty set as an element. It can happen. Okay. So, f of 3 for instance in this case would be the set 1 comma 2, f of 5 will be the set 1 2 3 4. So, this is a good example of an index family of sets. Now, coming back to the original theme, that is to break up a set into pieces that are disjoint and together is the whole set. Well, that is what is called a partition. A partition of a set A is an index family of non-empty subsets A I such that A is equal to union of A I and A I intersection A j equal to empty set for I is not equal to j. So, what we really want to do is, here we do not allow, in the definition of a partition, we do not allow multiple names for the same set. So, what you are really doing is, you have this mother set A and you are breaking that set up into multiple pieces such that each piece is referred to only once. That is what a partition is. Best way to understand it is to see some examples. Well, let us consider our mother set to be this set of 4 elements: star, triangle, square and diamond. Here are some examples of partition. Here is a partition of that set into 4 pieces, each piece has only one element and exactly one element. The second example, you are breaking up into 2 pieces. The first piece has star comma triangle, second one has square and diamond. In the third one, you are breaking the first piece as 3 elements and the last piece as just a single element. It is an interesting exercise to figure out how many partitions of a 4 element set are possible. Think about that for a while. It's going to, it's a lot of fun. Okay. Here is the final part of this video, and it is a major theorem, in the first major theorem of this course. There is a one-to-one correspondence between equivalence relations on a set A and partitions of A. Okay. This statement itself seems to be imprecise and vague. What is a one-to-one correspondence and what does it mean? Well, what this says is, given a set A and given an equivalence relation on the set A, I can associate a partition F of A. I can break up the set F, break up the set A by a partition F. So, given any equivalence relation, there is an associated partition. Also, given a partition of a set A, there is an associated equivalence relation. Starting from a partition, I can go back to an equivalence relation. And not only that, this one-to-one correspondence just means that this association is bijective. Given an equivalence relation, it is mapped to a unique partition, and given a partition, it is mapped to a unique equivalence relation. And if you start with an equivalence relation, get a partition, go back to the equivalence relation, you get back the same equivalence relation. That means 2 different equivalence relations go to 2 different partitions, 2 different partitions go to 2 different equivalence relations. So, one-to-one correspondence is just a long-winded way of saying bijective correspondence. That means, on the collection of all equivalence relations, I can define a function whose target is collection of all partitions, and this function is bijective. That is what this means. Now, a couple of years down the line, if you ever reminisce about this proof, you will think that this is actually a trivial theorem. There is nothing much to it, it is not saying much, it is an absolutely trivial theorem, but we are not at that stage. So, I am going to treat it with respect and give you a full proof, all lemmas and breaking up into parts and all that. It is going to be a, I am going to give a somewhat long proof. I suggest that after you watch this video, find a nice tree, assuming it is not too hot or rainy or anything, sit under the tree and just contemplate over this proof till you realize that okay, this is actually a trivial theorem, you do not need to provide such an elaborate proof for this except for the first time, of course. So, I call this the tree method. Many things in mathematics can be understood only by the tree method, that is sitting in under a tree and contemplating over the concept for some amount of time. Okay. So, first lemma, if you have two equivalence classes that are not equal. So, I will not repeatedly write, the setup is you have a set A and an equivalence relations tilde on it. Okay. So, what this first lemma says, that if you have two equivalence classes that are not the same, then they are in fact disjoint. So, either two equivalence classes are equal or they are disjoint. I mean, this is crucial because we want to get a partition out of an equivalence relation. Well, how do you prove this? Well, let us open up a blank page and let us think about it. So, we are given two equivalence classes A and B, and we are given that A is not equal to B. Well, the aim is to show that A intersect B is empty. What we will show is the contrapositive. What we will do is, we will assume that there is an element C which is in there in A intersection B, and then we will show that A is in fact, if C is there in this, then A is in fact equal to B. Note, this is not a proof by contradiction, I am proving by contrapositive. I am going to show that if the intersection is not empty, then A is actually equal to B. This is a proof by contrapositive. Okay. Okay. What is the meaning of C is in A? What does this mean? Well, this is just means that A is related to C. Why? That is the very definition of box A. Box A is the box of all elements in the set A which are related to little a, right. So, A is related to C. In a similar way, C is related to B, because the definition of box B is the set of all elements in A that are related to B, right. Notice that I have intentionally skipped a step. I want you to sit down and think which step I have skipped. It is something to do with symmetry, just think about it. Now, transitivity tells you that A is related to C, right. So, that means that transitivity tells you A is related to B. Okay. So, in other words, A is there in box B and B is there in box A, right. So, which means that box A equals box B. Again, I am actually skipping a step, but this is actually a trivial lemma, and writing any more is just going to make you bored. Just figure out how I got this, that box A equal to box B from what we have established so far. So, what this shows is the moment you have one element in common between two equivalence classes, then both equivalence classes are one and the same. Now, I can prove one part, partitions form an equivalence relation. Let tilde be partitions from an equivalence relation. Let tilde be an equivalence relation on a set A, then the set of equivalence classes forms a partition of A. Specifically, the collection of sets box A in A is a partition of A. Okay. We need to show two things. Every element of A is in some equivalence class. The equivalence classes are disjoint. Okay. Now, the fact that equivalence classes are disjoint is just what we just established now, right. We just established that if you take two different equivalence classes, then they are either equal or disjoint. Now, the fact that every element of A is in some equivalence class is really easy. Take any point in A, by the definition of equivalence class, A is an element of box A, because box A consists of all the elements in the set A which are related to A. In particular, by reflexivity, A will be in this box. So, that means every element of A is in some equivalence class, and as I said, the second point is just the previous lemma. Thus, the set of equivalence classes form a partition of A. Hey, wait a second, I am trying to pull a fast one on you. Just think about this for a second. What I have really shown is, if you take the equivalence classes, then the union of those equivalence classes is the set A, which is a property of partitions, and I have also shown that distinct equivalence classes are disjoint, but a partition by definition is an indexed family. Here I do not see an indexed family, I have just given a collection of sets F, right. So, let us try to fix this. Let us try to fix this. How do we get an index family from all this? Well, let F be by definition the various equivalence classes as A runs through A. Okay. Now, to get a partition, the natural thing to do would be to index this set F, and we are done, because the only difference, only thing lacking in the previous proof is the lack of an index. We have not given names. Well, there is a natural temptation here. Why not just consider the function f from A to the family F given by f of A equals box A. Why not just index this family by the elements of A itself? Please pause the video and think for a couple of minutes what goes wrong if you index this family by A itself, by the set A itself. I hope you have thought about this for a few minutes and have realized that what goes wrong is that it is quite possible that f of A equals f of B even when A is not equal to B. That is a crucial property of being an index set, is that f of A should not be equal to f of B when A is not equal to B. This happens precisely when the equivalence classes of A and B are exactly the same, or in other words, if A and B are related to each other. How do we fix this? Well, it is not hard at all. What you do is you cheat. You cheat by setting the index set to be f itself, right, and consider the function f from f to f be identity. That is, the element that gets mapped to the equivalence class box A is box A itself. So, this is a minor technical point, because we have chosen to define partitions as index sets, we are duty bound to give an indexing on the partition obtained by an equivalence relation, but that is not really difficult. You can always index a set by itself. The elements themselves are names of elements, right. So, it is not really that surprising that this is possible, but nevertheless it is a bit amusing. So, let us continue on with the main thrust of the proof. I reiterate again, this is just a slight technical detour because of the way we have defined partitions. Some authors do not define partitions as index sets, they do not have to take care of this small annoyance that crops up. Now, what is the other part of this? Start with a partition on a set A and we have to get an equivalence relation. That is, we define a relation on A by A is related to B if A and B are in the same subset of the partition. Now, the fact that this is an equivalence relation is utterly trivial. For instance, reflexivity is obvious because A will be related to itself because they are both in the same subset of the partition. Symmetry is equally obvious if A and B are in the same subset, B and A are in the same subset. Transitivity is also obvious if A and B are in the same subset, B and C are in the same subset, these two subsets have to be the same because it is a partition. You cannot have two elements in common with two different subsets in a partition, right. So, the fact that this gives an equivalence relation is really trivial. So, what have we achieved? Starting with an equivalence relation, we have obtained a partition. Starting from a partition, we have got an equivalence relation. And finally, there and back again, start with an equivalence relation on a set A and let P be the partition of A induced by the equivalence classes. Then the equivalence relation induced by P is the same as the original equivalence relation tilde. Again, the proof of this is an utter triviality. How do we get the equivalence relation? How do we get the partition? Well, the partition consists of equivalence classes. Okay. So, let's say that let's call tilde 1 to be the relation got from this family P, this partition P. Then when is A related to B via this tilde 1? Precisely when A and B are in the same subset of the partition. Well, when are A and B precisely in the same subset of the partition? Well, precisely when A is related to B in the original relation tilde. So, this shows, this short argument shows that if you start with an equivalence relation, you get a partition, then you get another equivalence relation, that equivalence relation is same as the original. Okay. Now, there is a converse to this which is equally trivial to prove. Start with a partition, you get an equivalence relation, that equivalence relation induces a partition, that gives you the same. So, the converse is also true. If you start with a partition, get an equivalence relation, get another partition, that partition is same as the original. And since the proofs of all of these are rather easy and they just use some basic properties of equivalence relations, I am going to skip that proof, but be sure to check that what I am saying is valid. Now, the proof is done technically. I want you to think about all the steps that have been done and realize that what I claimed originally has in fact been backed up by a demonstration. That is, there is a bijective or one-to-one correspondence between equivalence relations and partitions. Think carefully which step justifies injectivity, which step justifies surjectivity, and what exactly the function is between the collection of all equivalence relations on a set A and the collection of partitions on a set A. Both concepts are the same. Now, what are we going to do in the future? Well, what we are going to do is we are going to consider the set A quotiented by this equivalence relation, that is A modulo tilde. We are going to consider that set and study the properties of that set. It is called the quotient construction, and this is a theme that will get repeated in various parts of algebra and topology as well, where you partition a set and treat each partition as an element of a new set. So, that will be it is something that repeatedly arises, and in the next few videos we will see this restricted to just sets. Usually you have additional structure, you have a group and you quotient by a coset, I mean you group, sorry, do not quotient, you quotient by a normal subgroup, you get another group. You start with a vector space and quotient by a subspace, you get another subspace. You start with a topological space and their quotienting is very interesting. You can create complicated surfaces using this idea of quotienting. That is not part of this course, you will see it in a course on topology, but the basic idea is exactly the same. So, we will see all this and more in future videos. That concludes this video. This is a course on algebra and you have just watched the video on equivalence relations.